Welcome to the last session of our first day of conference. My name is Nadia Jamude Garcia, and the main topic of this session is planners. The session will take around 1 hour, and we will have presentations about the results of 3 ROS-IN focused technical projects, where we will talk about 2 different types of planners. On one hand, about task planning, on the other hand, about path planning. Just as general information, remember that during the sessions, we will have the live discussion panel available, and you can vote for our poll post during the full session, and also you have the opportunity to ask questions to our speakers. As we have for this session a pretty compact agenda, we will move to the discussion around the part of the questions and the answers. Yeah, this is everything from my side. Then let's start with the technical content. I would like to introduce our first speaker. He is Christopher Benson from the Chalmers University of Technology, and he will present his project about sequence planner for intelligent automation control. Then please, Christoph, if you are ready, the floor is yours.
Thank you. Can you see my presentation?
Yeah, I can see it.
My name is Christopher Bengtsson. I'm an associate professor at the Chalmers University of Technology in the Division of Systems and Control. And this work is partly funded by the ROS-IN project, but also other research funding from Sweden, and especially from Volvo Trucks have been highly involved in this. And it's about a tool called Sequence Planner, which we sort of call intelligent automation control. And what do we actually mean with intelligent? I sort of like this definition from Thomas Malone. So specialized intelligence is the ability to achieve specific goals effectively in a given environment. And I think we are sort of in the specialized intelligence category. And I like this notion that given some kind of state where we are, we have a system that can actually reach some goals or different goals, even if the environment is changing a little bit. And it's very true for when we're talking about planners, which this is about. So Sequence Planner is a tool that we've been developed for maybe 10 years. Initially, we're coming from the automation area, so it's a lot about gathering data and analyzing automation systems, running optimization, energy optimization, but also control, so we can use this running with sequences. But in the last 5 years, we have been working with more intelligent systems. So this is like bin picking system where it sort of can gather data and run the system. So we're actually controlling this with the Sequence Planner and using ROS2. You can see this is we are assembling an engine, and there's a lot of things going on there. We have robots and we have nut runners, we have operators and things going on. And the whole idea and the system is controlled by giving the system goals continuously in the system. And that is how we drive the system. And so I want to just talk about what do I mean with this traditional automation and intelligent automation. And when we talk about Sequence Planner. So for me, intelligent automation or traditional automation is all about the sort of the intentions and goals of the system are predefined. But in intelligent automation, the intentions and goals of the system can change based on the changing environment. So when you program a PLC, for example, it's very predefined. You have well-defined sequences. And these are usually very hard-coded. You can have a multiple of them, but usually you know exactly what you want to do. You have an initial state, and then you have a sequence, and then you produce something. But in intelligent automation, you need to have many generated control sequences. Maybe they can be hard-coded. Of course, you can make a system appear to be very intelligent, and I would say that is intelligent. So you have thought about all the possible situations to reach a goal given variation. But you can also, as in our case, have a automated planner that figures out how to reach a goal. Also, in traditional automation, if you have unknown changes to the environment, it usually results in some kind of failure, alarm or warning, and the system stops. And then you need to go in and restart the system. So in automation and production, that usually means you have to take the robots back to the home position, remove all the products, and start from some kind of initial state. But in intelligent automation, I would say that unknown changes to the environment needs to be handled by the system in some way. So either you try to replan all the time to trying to figure out how to reach the goal. Sometimes it's not possible, and then you need to do some kind of smart recovery and restart. Maybe tell the operator to do something to actually, so you don't need to take everything back to some kind of initial state. And also in traditional automation, the system cannot learn new things really. And I think intelligent automation, it doesn't need to be like that, but in many cases, I think the system should somehow learn something. So we have been working with this for the last years. And in this case, we are using ROS-2 and a path planner called IPS, which is online plans the robot motions. And you can see that in this case, we have some kind of thing in the way, and then the IPS can immediately find that, okay, it cannot find a path. So it finds that under a second, and then it can, sequence planner can replan and figure out, okay, I don't really need to take these bolts now, or I cannot do that. So it continues with what it can do, and immediately when the system discovers that the pipe is not in the way, it can continue, because the goal is that all the bolts are tightened. We have started a real demonstrator of this, but due to the COVID situation, we only have this demonstrator right now. But it sort of shows that you can replan. Another example where we have these goals, or we call them intentions on the highest level. So this is we have some robots, and we want the goal or the intention of the system is to have 3 cubes of different color. Three cubes of different color in the system, and then we say that the intention is this, and then the system figures out how to do that, and it can take in cubes. It doesn't know the colors; it has to take a picture. And then it finds a red cube, and then it finds another cube and see what it is. But it wants to have 3 different cubes. So it was another, so it works fine. But suddenly it finds another cube, and it's a blue, and then it figures out, okay, I need to put this out of the system and do this sequence again and figure it out. So I would say that, especially in sequence planners case, it's all about this online planner that almost like receding horizon planning continuously replans if it doesn't find the goal according to the plan it has. So this is another situation where we want to sort the cube. We don't have any collisions in this system, but now it worked. We could sort the cube. And then I force the system, I just remove one of the cubes. So now it starts sorting, and then I go in and just take away the cubes inside the state of the system. And then it immediately figures out, okay, that cube is gone, I need to add a new cube to the system. And then it can continue with trying to reach the goal. So this is examples of the need for some kind of automatic planner when things changes and we need to cope with situations that we didn't really think about when we programmed this system. So what about planning? When I think about planning, we can see that we have 3 different levels of planning, and especially when we come from the automation side, as we are doing, it's a lot about the details on the lowest level. So for us, we have some kind of intentions where we say that the systems, we have 3 cubes of different colors. We have operations. For example, it's pick cube, scan cube, remove cube, and then the resource levels are the bits and bytes and sending signals on a very low level. And there are some planners already mainly for if you have a single robot. And so on the intention level, you usually have some kind of hard-coded product recipe. But in sequence planner, we have a high-level optimizer, or we can also have a little bit more hard-coded logical intentions there as well. Then in most planners, the operation is the planning layer, where you have a planner, and we also have a planner, which is a bundled model checking planner, and we continuously replan if something goes wrong. But the big difference for sequence planner is that we also have a planner on the lowest level, where most planners have hard-coded sequences. You have Python code with if statements, or you have behavior trees, for example. But when we come to automation, we have a lot of interacting devices. We really need to plan on the lowest level because it's usually where it sort of hangs everything. So sequence planner have this high-level optimizer, which states what goals do we want to go on the intention level. The operation planner plans and figures out what goals do we need on the active planner. So pick one thing, plan one thing, and on the lowest level, it communicates on the ROS drivers with goals and measure state. And all of these are sort of shared, and we have a shared state. So it's a very much state-based control system. And also how we communicate is very much state-based, which has turned out to be very useful when it comes to this automation solution. So it's a state-based, and we have guards and actions and goals, and we will continuously replan when the outcome does not match the current plan. And if we don't find a plan so that the operation fails, and then we try to replan, we try to reach another with other operations, or if the intention we cannot find that anyway, we have sort of everything fails, and then we can tell the operator that something is wrong. We are using an off-the-shelf bounded model checker, a new SNV or a new XNV, actually. So it depends on what we are doing. So we are using that continuously, trying to find a plan using counterexample, and it's working really well. We can plan 100 and 200 milliseconds for a plan and generate new plans all the time. So the ROS-IN project, we has completed the milestone 1. So the ROS-IN was not so much about the planning part, but more about the documentation. And one big thing was to go from Scala to Rust. We have been implementing a lot in Scala, which is a JVM language. But 1.5 years ago, we changed to Rust, and we were really happy with that. So we have completed that, and we also implemented a new Rust binding, which you can check out. There are already a Rust binding, but we had to update it for Eloquent and Foxy, and we didn't. We also wanted a system that can be used without Colcon, so we can use it both with and without Colcon if we want, and it sort of supports a good Rust binding. We also are currently working quite a lot with modeling support. Right now, it requires quite knowledge about how the system works. So that is what we are working with. So the modeling right now is just you write Rust code. In this case, we are having a DSL to write different predicates and creating variables. And we will also work during the next year a lot with the examples, documentations, and tutorials to make this useful. So the main target is to let AB Volvo or Volvo Trucks use this and be able to create new systems for their sort of future automation systems, where they have both robots and AGVs and these kind of devices which needs the kind of replanning and also the support to integrate cameras and everything that ROS is really good at. And so Sequence try to keep track of all the state and update it and plan in this environment. Okay, that was my presentation.
Thank you so much, Christopher. Really nice presentation and really promising approach. Really like it. Thank you so much. As I say, at the end of the session, we will have time for questions. Then I would like to switch to our next speaker. He is Alessandro Umbrico from the National Research Council of Italy, and he will introduce us ROS-IN, a timeline-based planning and execution framework for ROS. Please, Alessandro, the floor is yours.
So, hi everyone, I'm Alessandro Umbrico. I'm a researcher at the National Research Council of Italy, and I here present some results of ROS-IN, which is a project funded by ROS-IN, and it concerns the integration of task planning AI technologies in ROS. So the context of this project is artificial intelligence planning, which really broadly speaking concerns the development of technologies that allow an artificial agent to have a model of a word and a model of the actions that the agent can perform and the effects of the action on the word. And then the development of technologies that basically allow such an agent to autonomously reason on the effects of his action, and so automatically synthesize plans that allow the agent to achieve some desired goal starting from a known initial situation. And in general, in the literature, there are several frameworks and several planning formalisms, and we in particular are interested in timeline, in what is called the timeline-based approach, because basically with respect to, for instance, the classical planning, it allows to overcome some restriction that have classical planning with respect to the features of the model and the problem that it can address. In particular, with timeline-based planning, we are able to reason on time and on concurrency of actions, and basically synthesize complex behavior as the synthesis of a number of features that evolve over time and that must be synchronized to achieve some complex behavior. And me and the group I work with have a long experience with the use of timeline-based planning in real-world application. There is a long thread in space-based application where my colleagues have achieved some relevant result in some project funded by the European Space Agency. More recently, I have also the opportunity to apply this technology in manufacturing scenarios where we have basically applied this timeline-based planning pairing to enhance the flexibility of, for instance, reconfigurable manufacturing systems, but also more recently in human-robot collaboration, where basically we have used these technologies to basically improve the flexibility of robots and enhance the capability of robots in collaborating with humans and achieve a better collaboration between the human and the robot that performs some common tasks. So in this context, why ROS-IN? The motivation of using ROS-IN was that basically we want to facilitate the deployment of timeline-based planning technologies in industrial scenarios, and using ROS as a middleware, I would say, as a framework, as a standard framework to deploy these timeline-based planning technologies, and so basically allow to realize some functionality to improve the flexibility of robot control, and so enhance the flexibility and adaptability of robot and collaborative robots in particular with respect to the dynamics of the environment and the specific scenarios. So in this regard, within ROS-IN, we have developed two packages, ROS packages, basically. There are one is called ROS-IN standalone and another ROS-IN based on ROS Java, because basically this framework is based on Java, and we have developed two different threads, one that allow programmers basically to use ROS-IN as a standalone package using ROS bridge features to interact with ROS, while ROS Java deployment basically allows a more fully integrated version and integration of ROS-IN with ROS as a native ROS node, I would say. But in general, so what you achieve, what you get with ROS-IN is basically this kind of acting node, where we have basically a deliberative process and an executive process that are implemented with ROS-IN that allows basically realize acting capabilities, where we have a goal topic, which is an input topic, where basically the node receive a high-level task requests that should be performed by the robot, and then this request is translated into a timeline-based planning problem that synthesizes a timeline-based plan that is then executed, and then the execution of this plan consists in dispatching some commands to some robotic platform, receiving feedbacks from the robotic platform that allows the executive to monitor the actual execution of a plan and adapt the plan if necessary, if something goes wrong. And then also to receive some observation about some conditions that are needed to observe in order to be consistent with the actual state of the world with respect to the execution of the plan. And just to give you an example of how these technologies can be used, we here consider human-robot collaboration scenarios that comes from a European research project called ShareWork, where we are actually deploying this technology. And in this case, we consider a collaborative scenarios where we have a human and a robot that together should collaborate and together assemble a mosaic like the one that you can see here. And basically, there is three types of boxes. The mosaic is built by moving boxes into a specific place. And there are three types of boxes. The orange box that can be moved only by the robot, the white boxes that can be moved only by the human, and the blue boxes that can be moved by both. And the role of the task planner is basically to decide which box is moved by the human and the robot, and find a collaborative plan that achieves some performance metric in sense of efficiency, and also the synergy of the collaboration between the human and the robot. So from with respect to the timeline-based specification, to model such a problem, we basically have to define a number of state variables that basically describe the behavior of the features of the environment, of the domain that we want to control. So we can have state variables that describe the process or the production process that must be performed, or state variables that describe the capabilities of the human and the robots in terms of the tasks that they can perform over time. And then we have transition between these values that describe how these different features can evolve over time. So which are the behavior that are valid with respect to the functioning. And also there are some values that are controllable, which means that the system can completely control the execution, while there are other values that are partially or uncontrollable, which means that the system can only, for instance, decide when to start the execution of an action, but it cannot decide when the execution is completed. Like, for instance, with the motion of the robotic arm, because it can be slowed down by the presence of the human, for instance. And then to coordinate these state variables, we have a number of synchronization rules that basically specify temporal constraints that coordinate the possible behavior of the state variables in a way that we can thus achieve the desired objective. And given this specification, basically the timeline-based solving approach is realized as what we said, a plan refinement search, where basically we have a set of timelines that must be iteratively refined until we have a complete set of timelines that achieve the desired goals. And during this search, basically there are two choices that can be made. One choice that concerns the flows, so which is the condition that we want to solve to refine the plan. And then the selection of which is the most promising partial plan that we have refined to find a solution, basically. And also we integrate some pseudo-controllability check in order to verify whether the plan that we are building makes some assumptions on the actual duration of uncontrollable values of the domain, in order that we are able to synthesize plans that are somehow robust or reliable with respect to the real execution of the plan in the real environment. The search basically is organized as a multi-objective search, where we analyze a number of metrics that characterize the quality of the plan that we are building, and try to find a good trade-off among these metrics in order to synthesize solutions that are not just efficient with respect to the planning process, but are also effective with respect to the actual execution in the considered scenarios. In particular, we consider as metric the efficiency, which is the make span of the overall plan that we are synthesizing. So in this way we try to optimize basically the collaborative process that is performed by the human and the robot, but we also consider the safety. And so basically we consider the synergy and the pace of the human and the robot tasks that are going to be performed simultaneously. And in this way we have we can reason on which is the pace of tasks or human and robot tasks that allow to reduce the risk of collision between the human and the robot while executing the collaborative process. Then this search is enriched with some heuristics, domain-independent heuristics that are built by analyzing the structure of the synchronization of the domain. In particular, we use a hierarchical modeling approach that specifies synchronization in a way that the values of the of the domain determine a hierarchical decomposition of the task. For instance, in this case, we can see that we move from the production level, where we describe the production process and the goal of the production environment, and we move down to the implementation of a particular production task and the low-level task that the human and the robot can perform. And this hierarchical decomposition can be used to extract some useful information that is integrated into the search in order to guide the solving process of the planner. Similarly, we can also have a decomposition graph of the different values that are part of the different state variables of the domain, and then this is information that is extracted automatically from the domain specification, and it is then used by the planner to enhance the solving capability of the planning engine. Then when we have a plan, and so we are ready to execute a plan, this is done with a closed loop control process where we have a clock that discretizes the time and generate a number of ticks that are some execution events that guide the execution process. And during each tick, basically, it is implemented a dispatching phase where the system decides which is the command and the task, for instance, that should be performed and should be then dispatched to the robot for the actual execution, which is also the task that the human is expected to perform. And then we have a monitor that manages feedback and observation from the environment in order to check whether if the actual execution of the process complies with the plan, and trigger a replanning event in case of necessary. And at this level, we also take into account the controllability information in order to adapt the execution of the task according to their controllability properties. So, for instance, as I said previously, we have controllable tokens that can be controlled by the system. So is it the system that decides when to start and when to stop the execution of a token, while we have other tasks like, for instance, the request of executing a task to the human, where the system can decide when to start and send the notification of the request, but the actual end of this task and the execution of this task is up to the human, which sends a feedback to the system in order to notify that he has actually completed the execution of the task. And then, according to this information, the system is capable of reliably execute the plan, reducing the need for replanning when some delays, for instance, in the execution of the human task are observed, because for temporal flexibility and the pseudo controllability property that we find into the plan. And here you can see a short video where we have we have made with our colleague from CNR STEMA within the Sherwood project, where we have evaluated some initial deployment of this planner into a simulated environment, because for COVID situation we had the possibility to make a real experiment. But in general, here you can see that there is a human and a robot that are collaborating, and so the planner has synthesized a set of timelines for the two agents that represent the task that the two agents are going to perform within the planning horizon. And here you can see some information about the planning process, where basically we have a heuristic distance evaluation, which is somehow a classical heuristic estimation of the distance of the plans that of the partial plan that we synthesize during the process to the unexpected solution. And then you here can see the evaluation of some of the metrics that we are trying to optimize within the planning process. One metric is, for instance, concerning the cumulative risk of the collaborative plans, where we can see on one side the heuristic estimation of the risk of a partial plan, and then you compare with the real risk that is achieved during the synthesis of the plan. But probably more interesting in this case, you can see the comparison between the make span of the human and the robot, in the sense the make span of the timeline of the human and the robot that is built by the plan during the search. And you can see here that the planner tries to keep the two timelines as close as possible until the end of the process, where he tried basically to minimize the difference between the make span of the robot and the human, in order to have a balanced workload between the two agents. And this is just to give you an example of how we are actually deploying these technologies in a real human-robot collaboration scenarios. And here are some links to the ROS-IN project that is publicly available on GitHub, and it is under Apache 2.0 license. And these are the link to the two packages that I mentioned, the ROS Java version and the standalone version. And there are some ongoing work concerning the modeling language of this tool. And now we use the domain description language, and some documentation can be found at this link. And so that's all for my presentation. And thanks for your attention. And if you have questions, I can answer next. Thanks.
Thank you so much, Alexandro. Really nice presentation and really impressive solution. Yeah. Last but not least, our last speaker for today, who closed this session about planners, is Cesar López Martínez from Nobleo Technology, and he will talk about coverage, path planning, and control. Cesar, if you are ready, you can start.
Yes, thank you very much. Let me see. All right, you can see now my screen, I suppose.
Yes, I can see it.
Yes, so I'm going to present about the FTP coverage path planning and control, and I'm part of Nobleo Technology since 2015, and recently I'm also a part-time assistant professor at the Eindhoven University of Technology. What I'm going to talk about in this presentation. So first, I'm going to give an introduction about Nobleo Technology, what we do. Then I'm going to talk about the first part, which is the full coverage path planning. Then I'm going to talk about the path tracking control that was also developed for this path planner. And I'm going to show some industrial applications and how we apply these concepts into some real life applications. And then we will have time for some discussion. So, Nobleo Technology, what we do, we provide solutions for autonomous intelligent systems, and this reflects the three main departments of our company. So autonomous mobility, intelligent software, and systems. And this is a couple to our three main skills, which are system development and integration, software, and sensing and actuation. So since I'm part of the autonomous mobility, I will give some more details about that. So here we see some example of the type of robots that we have worked on. So we have helped our clients to develop these prototypes. So these range from at the beginning from some development mule for mobile robotics. But we also have worked with aquatic drones, with tank cleaning applications, with logistics applications, agricultural robots, also this palletizer for logistics in warehouses. And recently we also started working in an autonomous street sweeper. So I'm going to show you a part of a promotional video in which you can see some of these applications.
For a decade, Nobleo Technology has been active in the field of autonomous industrial robots, providing robust and reliable robotic solutions to automate dull, dangerous, and sometimes dirty jobs. Our cleaning robot, Emma, is the forefront of autonomous tank cleaning. The robot shown later in this video is the continuation of this development. The fully automatic waste shark vessel cleans harbors and waterways around the world. Existing warehouses can be transformed into autonomous logistics centers with the Nobleo Autonomy upgrade kits.
All right. Now, the next topic, I'm going to talk about the first package that we developed for this FTP, the full coverage path planning. So basically, what's the motivation to work on this package is that there was not, let's say, a quality assured implementation of a full coverage path planner. So given a map, we would like to have an algorithm that fully covers the accessible space on this map. And we would like to integrate this with the standard ROS stack. It should be computationally efficient and reduce the double passes that the robot will follow. So we basically looked into the literature, what were the available algorithms, and we have decided to choose this one, which is based on backtracking spiral algorithm. It's a very simple one, but it's very effective. So basically, based on the obstacles that the robot has in the surroundings, it determines to move forward, right, or left. So you see here one example how that would work. So in this case, if we start in the top left corner, the algorithm will return the spiral in light gray. And then when there is no more progress, a start is used to move to the next available cell. And then the process is repeated until the full space is covered. So here is one example of what type of paths are generated with this package of a robot of 20 centimeters in the map of our offices. So one of the things that we notice also is that in real applications, many times the tool that you are going to use to cover the space, it doesn't have the same radius as the total robot. So we also added support for these cases. And to give you one example, what would be the difference is that if we have a robot that has a 7 centimeters radius, if you use the same tool radius, then you obtain this kind of path, but maybe the tool is smaller. So you don't want to be conservative. So we included this such that the area is covered as desired. Now, once we have a path, we would like to have an algorithm to be able to track this path. And surprisingly, there was also not available as a ROS package, a reliable tracker. And that's why we also developed this as part of this FTP. So the goal is to accurately follow a given path. So we would like to have a quality assured implementation, integration with a standard ROS stack again, and we would like to have a predictability and repeatability, which is important for industry. So we have decided to go then for this architecture in which we have then a global planner, which in this case is the full coverage path planner. Then we have an interpolator, which will generate a moving point on this path. And then we have a tracking PID controller that will compute the velocity commands for the robots. So the interpolator will make sure that the behavior is predictable and repeatable. And with the tracker, we can tune it for a high performance. So the interpolator generates a point that moves along the global path with a constant velocity. So this is an example of such a point moving through the path. So the tracker, so we have two modes. In the first mode, we call it the carrot mode. So basically we compute a control point, which is at a fixed distance from the baseline of the robot. And the idea is to be able to track the global point that is moving. And we do this via 3 loops. So we use the errors, the translational error, the lateral error, and the angular error. And all these loops are tunable. And you can also enable or disable them. So this is an example of what kind of performance you will get with this. So what you see in light gray is a trace of the area that is being covered. And you see that the robot is basically following the point at a distance, because yeah, this is part of this carrot mode. One of the things that you notice is that in the corners, the robot cannot reach that because of the structure of this method. So therefore, we have also expanded the tracking PID to do a base link tracking mode, in which the idea is that the robot can follow the path with the base link. We do that in an indirect way. So basically, we compute a projected global point based on this global point on the path. And now we are going to follow, instead of the global point, the projected global point. And we are going to do that indirectly. We will end up making the base link to follow the global point. How this looks then in the same simulation that you saw before. So basically now the robot is able to reach the corners. By the way, I forgot to mention, we also modify the interpolator such that it stops on the corners. We included acceleration and deceleration limits, and also in the rotation. So basically now we have an arrow that is moving. Now, how does this look then in some industrial applications? I'm going to show you a couple. So the first one is tank cleaning. So in this case, we have this robot that with a magnets, it can adhere to the walls of big oil tanks. And for this specific line, we implemented a zigzag trajectory, but this can be applied also to the full coverage path planner. And we use the tracking PID package. And here you can see the type of response that you can expect. So what you notice here, for instance, is that because of the gravity, the robot has a disturbance, but because of the PID controller, the robot ends up moving at an angle, but still following the desired trajectory. So this is an example how this tracker can function in these kind of systems. This is the next example is we apply this to aquatic drone for waste collection. So this was a very challenging application because this drone has a lot of disturbances, and that was actually making the performance of the tracking PID bad. What we did here is that we added a coupling scaling between the angular error and the translational error, such that we can reduce the overshoot in the system. So in this video you will see it's actually quite a challenging example. So you see that there is a lot of wind because I'm in the Netherlands, and that's quite normal here. You see that it's perturbed quite a lot, but then the robot is able to recover. So basically, when we sense that we are far from the point, we have a scaling that will give priority to the angular controller, the angular loop. Yeah, so that brought me to the end of this presentation. There's two packages are available online in our GitHub account of Nobleo. Thank you very much.
Thank you so much, Cesar, for your presentation. Really interesting. I will kindly ask our speakers to all switch on the cameras. I think you all made really clear presentations because we got only one question from the audience. The question is to Alexandro, and it is possible to change the executive component in ROS-IN without changing the delivery component, something like a plugin?
Hi, Thanks for the question. In general, yes. So the framework has been developed in, I would say, in a modular way. So you can change somehow some key component of the module without working locally on some part of it. So in general, so the executive can be extended or replaced with more other modules that can be developed. Maybe that with respect to other aspect of the planner, for instance, like heuristics or strategies, is more complicated, I would say, but in general is something that you can do, of course. And if you, I don't know who made this question, but if some assistance is needed, you can send me an email. I can give him more information or more detailed insight to where to put the hands, basically.
Thank you, Alexandro. Also, I have a question to Cesar, maybe a bit delicate question. What about the ROS-2 support, the ROS-2 portability of your tools? Is something in your roadmap?
So when we started this FTP, that was 3 years ago. So that was not in the initial plan. But we, as a company, we are definitely interested to move to ROS-2. And that means that all the tools that we support will also be ported. I cannot say that it's going to happen this year, but yeah, definitely it will happen.
Also, now a new question to Cesar. Is FCPP compatible for 3D path planning, for example, agricultural applications?
Not at this moment, no.
And
So,
do you go, oh, sorry, yeah, go
so
ahead.
it was designed for planar movement, yeah.
And do you consider the dynamic of the robots in the controllers?
So the controller is a PID controller that measures the, so it uses as an interface the velocity. So basically it can be tuned. So we don't use, so basically depending on the dynamics of your robot, you can also tune your controller, but we do rely on a velocity interface, which means that also part of the dynamics are being controlled in that loop.
Mm-hmm. Also, another question about path planning. Yeah. Can the robot avoid an unexpected obstacle and then eventually recover to the original path?
Yeah, that was discussed at the beginning of the project, also during the proposal. But then, since the focus was on, let's say, repeatability and predictability, so it was decided that obstacles on the way were not considered. So, in this case, the interpolator has a mechanism that it can be stopped. So if it's connected to another node, for instance, that can do the detection, then the interpolator can be paused and then it can be resumed, basically. So in this case, the kind of behavior that can be incorporated is that the robot stops until the obstacle moves and then it can resume.
Thank you, Cesar. Maybe also one question to Christopher. You mentioned that you have already implemented a DSL to define the main task planning. Are you also integrated some code generators? And if yes, which kind of code are you auto-generating?
So for the models, we are not auto-generating now. We have plans for auto-generating ROS nodes for the detailed resources, because since we need a quite detailed model of the behavior of on the lowest level, it's usually you need also you almost already have what you need in the ROS drivers. So it is possible from our models to generate the ROS drivers and generate everything. But we haven't done that because in the end, you anyway need to interface it with the real robot or real hardware somehow. So in the end, we didn't do that.
Okay, we can move to the pool questions about task planning. There was a question about what are the main research challenges for task planning, and the 50% of the audience say that the tight integration of planning and perception. What do you think, Christopher?
Yes, I think that is key because everything to make this in reality, you need to get the reality or the state somehow, what is going on, and the perception is the how you do that, and especially how you use cameras and gathering data. So I would say that is the key, especially how we do it, because we always try to replan and figure out what is going on. So then we really need a tight integration with what the perception sees, what the planner wants to do, and what the goal is. So I think that is the key, and we have worked quite a lot with that actually, to include different types of vision systems into our different examples, just to always have that in our programs.
And maybe Alexandro, you have also some comments on that?
Yes, I would say that for my experience, basically I have mainly developed these technologies when dealing with humans. And in this sense, I think that perception is a key to enhance the collaboration, in the sense that, for instance, perception is useful to autonomously check whether the human is doing the task that the task planner is expecting to do. So in order to have a more robust way and more adaptive way of synthesize the collaboration in this case. So have more also to support a more natural, I would say, more adaptive behavior of the robot with respect to the actual behavior of the human, and somehow try to keep the human central to the work, and be not doing his task, and so let the robot adapt to the human and not vice versa. So this is just my comment, I would say.
Yes, another thing, I think that especially when we see these kind of perception or sensors that are coming now, it becomes harder and harder to use traditional way of programming these systems. And I think that's what industry sees. So they think they can solve everything with these nice sensors, but then they try to integrate it with more traditional automation or robot programming standards, and it never works because it doesn't work. They need some kind of algorithms to solve it. So I think that is it's a very important part.
Yeah, also about shortcomings of path planning and automatic collision avoidance. Maybe Cesar, you can also say some words. The majority of the people say that the main shortcoming is the integration of the actuators and the sensors, and how to calibrate the full setup together. What is your opinion on that?
Yeah, actually, in our company, we have helped a lot of clients to develop the prototype. So basically, they come to us with an idea, and then we take that idea to a prototype, and so I would say 70% of the work it goes to find the right actuators, the right sensors, do the whole integration test on the field, and then when you have your hardware properly functioning, then you can start trying your algorithms, because you can also do a lot on simulation, but you shouldn't spend also too much time there, because once you go to the real robot, you will discover new kind of behaviors, and then there is the second stage, where is the theoretical boosting, and that also takes a lot of time. So basically, debugging all these specific problems.
Thank you so much. Yeah, if we don't have more questions from the audience, I would like to thank again our great speakers for today's sessions. Also remember the people that with the Swapcar platform, you can contact to our speakers all the time. And yeah, I would also to thank everyone for joining for this session today.